Okay, so in this exercise, now we're going to focus with mice. So we have the following situation in which we have a laboratory with a mice population of 60 total mice. 30 of them are going to be healthy, 20 of them are going to be sick with sickness A, 10 of them are going to be sick with sickness B. So we can just denote the following, right? We denote the following. It says H is going to be for the healthy ones, and we have 30 healthy mice, so we can do that. A is going to be for the ones with sickness A, is going to be from A1 to A20, and B is going to be the same thing, but for B10. So we have 16 mice total, and then they tell us that we select 10 random mice. So from 16 mice total, we choose 10 random mice. So in this scenario, there would be 60. The binomial coefficient will give us how many ways can we select 10 mice out of the 60 group, right? That's going to be the binomial coefficient, and that would be in case, well, simply put, the size of omega. Remember that omega are all the possible cases, all of them. So now in exercise A, they're asking us to do a discrete probability space that models this situation completely. We have to explain how the sample space. We got to give a sample space and define omega properly. That includes all the combinations possible with the mice. And so, let's do that. So the first thing we have to understand is we want to basically describe what omega is. So omega is going to be equal to the set of every single sample space that is a subset, right, of all the three groups together, right? So in this case, it's going to be G. This is going to be H, sorry. This is going to be A. This is going to be B. So in this case, I made a little example in which we say, imagine we know we have 30 healthy mice. Imagine we take 4 out of them. So we get 4 here. And then we have the 20 sick mice with A. So we take 3 of them. Same with B, another 3 of them. And when we add these up, they're going to give us 10 mice, right? In this case, we took it from this whole group, right? So we can see this is a functional full group like so. So we want to unite them. So S is going to be this. So it has to be the union of H, A, and B, right? That's it. Such that the size of the sample is equal to 10. And this will describe all the possible combinations. That's it. It's as easy as that. Now, we want to explain another situation. Let's say that now we want to have a case. So let's say we have a case in which we have, I don't know, let's say we have 5 or let's do 8. 2, 3, 4, 5, 6, 7, 8. And then 1 red and 1 orange, right? Imagine we have this case. So that means we have 8 healthy mice, 1 mouse with sickness A and 1 mouse with sickness B. In this case, that will be our case. Sorry about the, yeah. Anyways, so if we continue with this, we can just denote a case as a simple C, right? And we know that C has to be within our omega, which is the set of all possible cases. So the probability, right, of X equaling C is going to be given by this, as we have a uniform, so to speak, probability, meaning all probabilities are the same. We have no different probability of choosing one mouse over another. We're gonna do the size of C over the size of omega, and it's gonna be for all C and omega. So in this case, if we want to actually find this out, we would just declare C, right? C, we don't know what it is because it depends on every case. But we do know that the size of omega, right, is going to be 60 and 10, right? So, simply put, it's simply going to be that. Now, let me just check something real quick. Sorry about that. That's simply it. So this would be the size of omega. And so this is all the exercise. We have created a sample space for omega that has all the possible combinations and describes them properly. And we have created a probability measurement on the space. The probability measurement will be this, right? And this will be the omega definition. So that's it for A. Okay, so now we're gonna do B. In this case, we have the following. It says we have to give an event where A1 is a subset of omega in a formula basically. And it has to describe the following, that at least one of the mice, one of the 10 mice, is sick. And we have to calculate its probability, right? So what do we do in this case? Okay, so we simply start with A1, right? And the first hint we can see is that A1 has to be a subset of omega, meaning A1 has to be an omega. So we start by saying that the sample that we're taking has to be in omega. So we say S has to be in omega, right? And now we're going to declare the actual property. So we do such that, right? And in this case, we're going to say, okay, we have at least one of the mice is sick. What does this mean? It means we take both groups of the sickness. So imagine we have, I don't know, we have a group A of sickness, and we have group B of sickness. We want to make the union between these two guys. So union, and this is gonna give us basically just a new group, right? Let's call it C in this case, which is a combination of these two, right? If you want to look at it in a more visual way, it will look something like this. You just color it properly. Oops. It will look something like this, right? That's what we want to do. So what we do is we say, okay, it means that at least one of the mice is sick. Okay, perfect. What does this mean now? Well, it means that whatever sample we have, the sick part has to be at least the size 1. So how do we do this? We simply say, okay, let's take the sample. Imagine we have a sample. So sample. And imagine we have 8, or let's just say, yeah, let me just make this circle a bit bigger. Imagine we have a sample, and we have 10 different mice, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's just put, well, let's do 8 actually. And let's put the last 2 over here, right? In this case, these 2 are going to be the sick ones. And we already know that this is C, right? So we want the intersection between S and C to be equal, right? We want this intersection for the size to be equal to greater than 1, because it says at least 1, so it can be more than 1 as well. So it has to be the size of this, right? So the size of, let me just describe this properly, of S intersection of C has to be at least greater than 1. So we can write that here. S intersection A union B has to be greater or equal to 1. And that's it. That's as easy as we can get it. And that's basically our definition of A1. So now they're asking us that we have to calculate its probability, right? How do we find it? Well, we can use the rule of complement, which states that A1 is going to be equal to 1 minus P A1C, meaning no. In this case, if we write it in formula form, let's do PA1. So we write this, probability of this, the probability of this happening is going to be equal to 1 minus the complement of this. And the complement states that this should be lower than 1. We know that we have no fractional numbers in probabilities. It's only integers, meaning that this is going to turn into 1 minus, yes, how many numbers that are integers are below 1 is only 0. So this will be equal to 0. And that's pretty much it. We have 1 minus this. And this is pretty easy to calculate now, because we know that in order for no mice to be sick, it means we select just healthy mice, right? So this is going to be equal to 1 minus PAC, which is equal to 1 minus, and as we already stated, we have to find the size of AC divided by omega. So in this case, it's going to be 1 minus, how many healthy mice do we have? We have 30. How many can we select? 10, right? So in this case, we're selecting how many, what is the number of different different cases where we can choose 10 mice out of the group of 30 healthy mice, right? Divided by 60 and 10, which is the full population. And this will give us a certain number, but in this case, we're not going to calculate it, but this is the solution. That's how you solve B. So again, we want to do another case where they give us another event in which it states that A2 should be a subset of omega, and we have to give it in the formula. And it says that more mice with sickness A as sickness B are selected. And we have to also calculate the probability. So what do? We first start with the event formulation. So we already know that it's going to be a sample that has to be in omega, and then such that the overlap between the S and A has to be greater than the overlap between, let me just erase this because it's going to be confusing, and just put dots, B, right? So how does this work? Simply put, imagine we have, again, an S, and we have, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, and we have some A ones, and the overlap has to be this. So the intersection between those two has to be this, and this is the size of 2, right? And there's no B, so the size of A is greater than B in their sample S. So in this case it works. So that's the logic behind it, right? But now we have to calculate its probability, the probability of A2. To find the probability of A2, we have to do A2 divided by the size of omega. We do know omega, the size of omega, which is this guy, but we have to define the size of A2. So how do we do this? Okay, so the first part is to understand we have to see, we have to like just think of combinatorics. So first of all, let's think, how many can I choose? Let's say, let's take the group of 20, which is group A, if I remember well. Let me see over here. So it says here, let me just copy this so we can remember and put it over here. So we know for a fact that we have group A. Let's start with group A, because it's a group that we're focusing on. And group A, we have 20 mice. So we can choose I amount of 20s, right? In this case, we can do the same thing with the group B. We can do this. And so when we do this, 10 minus I minus j. So how does this work, right? Let me explain this to you. So in this case, we start with the summation, right? The summation of I equals to 1 to 10. So what does this mean? It means that we're choosing how many i's we can select. So in this case, we're saying, okay, how many, what are the different combinations I can take, where I take one mice out of the 20 sick mice from the group A, and then I scale it every single time, because it can be from 1, 2, 3, 4, up till 10, because we can select 10 mice in total, right? And the same thing over here, we're going to do the same summation, but in this case, we're going to do I minus 1, because we know for a fact that I is going to be linked to A. So let me just rewrite this. It's a bit confusing. I know it's a bit confusing. So let's start with the summation, right? In this case, we're going to use A's instead of I, so we can understand better. So we can, because we know A is connected to small a, right? So the first thing we have to do is saying, okay, we select A equals 1, and we can select up till 10 sick mice in group A, right? And we want to do the summation as well, but this time for group B. And we want group B to be less than group A, right? So we're going to take A minus 1, because that's going to assure us a case where it's going to be less than A. So, and B starts from 0, because we can select also 0 B mice, right? And then we're going to do simply put the combinatorics, which we say 20 and A, this is for A. Then we do 30 for B, right? Oh, 10 for B, sorry, not 30. And then we do the same thing now for the rest 30 mice. In this case, if we selected less than 10, 10 is the maximum we can take, and we want to remove the one we chose from A and from B. So that's going to be our, simply put, our solution. So if we want to find the actual probability, we would take this, right? Delete it, equalize it. And in this case, it's going to be the size of this, so it's going to be 60 and 30. So that's going to be our solution, simply put. So it's a bit confusing, I know, but just try to think of it from one step at a time. We first think of, okay, how many different mice can I select? So I can select up till 10. So I do a summation till 10, starting from 1, right? Because I had to select at least 1. And then I do the same thing, but for a lesser number, in this case. So A minus 1, so it's less than A, and B starts from 0. And then we just put our different groups accordingly. That's it. Okay, so this is the last exercise of these mice. So we're going to let a new population be living together, such that each mouse with a sickness infects all the others that don't have this sickness. So imagine we have, so you can have a physical view, a visual representation. Imagine we have 4 let's say 5, right? Let's say we have 5 here that are healthy, right? And we have A that are 3 and B that are 2, right? So in this case, there are 10 total mice in our S. So in this case, this is going to be S, right? And in this case, we're going to see, okay, so in this case, we're going to see that B affects all of, is going to infect all the other guys, right? So in this case, oops, it crashed. Okay, amazing. Let's see if it stored it. Oh, it didn't save it. Amazing. Sorry about that. It just crashed for some reason, but let's do the same case. 1, 2, 3, 4, 5. And B, I think, was A was over here. 1, 2, 3. And B was over here. Let's do a simpler case. We only have 1 and 1. So it's going to be 8. 1, 2, 3, 4, 5, 6, 7, 8. This is going to be a simpler case, actually. Understand what's going on. So in this case, right, B is going to infect all of these, right? All of these he's going to infect. Right? So let's do this. He infects all the other guys. And the same for the red, right? Same for the red. In this case, I'm gonna, let's see if I can do a little trick here. I don't think I can, rotate it properly, but just take A and then just put it here, right? In this case, it's all gonna be red. Red. Thank you very much. And also, B, well, A is gonna infect B, and B is gonna infect A. So there's a lot of infections going on. So that's basically what we want to do. Like everyone is infecting everyone, and that's it. So we want to give this event in a formula. So how do we do that? We simply say A3 is equal to S being the part of omega, in omega, such that, and here comes a part, new infections only happen, right, as long as the 10 mice don't belong to the same group. So imagine if we only had 10 mice in group A, they wouldn't be able to infect anyone. If it was H, if all of them were healthy, no one would be able to infect the other one. And if B was, all of them were 10 and they were sick with B, they wouldn't be able to infect those guys either, anyone else, because there's no one to infect. So in this case, we want to take the complement. So let's take the complement of this. A3 complement, right? Where nobody gets sick because everyone has a homogeneous group. So we can say that this, right, is going to be S is this, meaning that S is going to be equal, basically, to the subset of A. So meaning all of them are going to be sick from A. Or, right, S are going to all be sick with B. Or the sample is all going to be sick with, or going to be healthy, sorry. Right? So if we take the opposite, the complement, so complement is going to be where they're not. And this is and H. So that's pretty much it, right? That's how we get it. Now, we want to see the case, and we want to actually get the probability. So we know for a fact, right, that PAC, well, PA we want to calculate PA3 is going to be the size of A3 and this. However, it's easier to use our other rule, which states that we have a complement. We can calculate this. We know for a fact that the size of A3C, right, is going to be equal to all of these. It's going to be the size of choosing, how you call this, the sample of 10, where 30 of them are sick with, 30 of them are healthy, sorry. So this is for healthy, plus, right, 20 and 10, which is going to be for A, I reckon. And then we're going to have 10 and 10, which is going to be C. Sorry, B. Meaning that this is going to be our size. So if we want to find this, it would simply be, you want to look at it in a more defined manner, like so. Oops. We just take and copy these little guys. Oops. Duplicate them, make them smaller. And then this is going to be 60 over 10. No, 30. If I remember well. So that's it. That's pretty much how you solve this one as well. So yeah, that's pretty much all the exercise of the mice. It's a bit complicated, but I think doable if you take your time. So that's it.